Alright, so in this is we're going to start looking at forces and Newton's laws, and my main goal for today is to kind of introduce what a force is and then kind of look at how we do forces, or what we do with forces, and how we start to identify some forces. So first of all, what is a force? Forces are everywhere in our world, and generally speaking, any push or pull on an object can be modeled as a force. There are two general types of forces if we wanted to break them down. One is what I would call a contact force. That requires two objects to be in contact with one another, and that force is related to that contact between two objects. If I was to do something like push a cart down the hallway, the force I apply on the cart would be a contact force. Friction is also another good example of a contact force. In order to have friction, two objects must be touching one another. The second type of force is what I call an action at a distance force. Our gentleman over there, Yoda, does a lot of this action at a distance force when he does something like lift a spaceship out of a swamp. When we talk about action at a distance, the force that probably you're all familiar with that's an action at a distance force is gravity. You don't need to be in physical contact with the Earth in order to experience the Earth's gravity. Try to throw a ball up in the air and see what happens. The ball will end up getting pulled back to the Earth. Action at a distance forces usually can be modeled by developing what we call a field. The technical term in physics is a force field for this, which allows us to begin to model how that force looks over various distances. The one thing to point out about forces is that forces are vectors. And that's going to become very important when we start to begin to add and subtract and work with forces. The forces not just have a magnitude but a direction. If I push with a force of, let's say, 500 newtons on one side of the cart, and you go to the other side of the cart and push with a force of 500 newtons in the opposite direction, nothing's going to happen to the cart, even though there are two forces applied to the cart. That's because the directions of those forces allow them to be canceled out. Now, when we talk about forces, what we can ultimately do is narrow down forces into basically one of three categories. These are what we call the fundamental forces. These are the ones in physics that we try to develop an equation to represent what that force actually looks like. And there are really only three fundamental forces. Ultimately, all types of forces are one of these three types of forces. One of them that we talked as the most obvious one is the gravitational force. That's what holds us to the Earth. That's what brings the ball back to the Earth when I throw it up in the air. The second one is what's called the strong nuclear force. This one's probably one that's not as obvious to us. We don't see it on a daily basis, but we see its impact on a daily basis. That's what holds the nucleus of an atom together, holds the protons and neutrons together inside the nucleus. The third type of force, our fundamental force, is what we call electroweak. And electroweak is really a combination of lots of different types of forces. Any type of electrical interaction, magnetic interaction, and the force that's responsible for lots of types of radioactive decay. Basically how individual protons and neutrons stay stuck together, not what holds the nucleus of an atom together. That's really this electroweak force, what we call the weak nuclear force. Of these three forces, the one that we actually know the least about how it works is the gravitational force, which to me seems very, very odd. The reason why it seems very, very odd is of these three forces, that would seem to be the most obvious one to me. We don't really know how the gravitational force works. If you've heard of an experiment by the Large Hadron Collider, the LHC at CERN, where they found a particle called the Higgs boson, or what some media articles were calling it the God particle. The reason why that particle is so important is it really starts to begin to explain how the gravitational force really works. Like I said, ultimately all forces are one of these types of forces. What I want you to know about fundamental forces is that there are three types of fundamental forces that we can basically take all forces and divide them as one of these three types. And so the number of different types of forces that actually exist is pretty small when you actually try to reduce it down to the smallest number. So one way that we use to begin to identify forces on an object and help us to solve problems dealing with forces is what we call a free body diagram. I used the example earlier when we talked about forces being vectors, that if I push on a cart with one force in one direction and you push on the same cart with the opposite in the opposite direction with the same force, the cart doesn't move. Even though there are two forces acting on the object, those forces cancel each other out. One way that we begin to identify these types of forces by using a free body diagram. So let's consider a block sitting at rest on an angled ramp. And so I have this block sitting at rest on the ramp, and the three questions I want to ask myself is, what forces act on the block? In what direction do those forces act? And what's the best way to represent those forces? So the three forces, there are actually three forces that are acting on the block right now as it's on the ramp. One of them is the most obvious force, and I'm going to put a dot down here to draw my free body diagram. And the most obvious force is gravity or weight. If we're sitting here on Earth, gravity is pulling the block down. What's holding the block on the ramp is gravity. The way I'm going to represent gravity is an arrow that points downward. Gravity is always a force that points downward toward the center of the Earth. The second force that I think is also relatively obvious is friction. If the block is not sliding down the ramp, there must be something keeping the block from sliding down the ramp. In this case, friction is the most logical force. The reason why friction is the most logical force is the block and the ramp are in contact with one another. If the block is not sliding along the ramp, and we know it probably should, if there's no friction, the block should slide to the ramp. So that means that friction is the second force that's acting on the block. So I'm going to put an arrow that points up the ramp. The reason, or how I know that friction is working in a direction up the ramp, is that, well, friction is a force that resists motion. If I just allow this block to slide the way it should normally slide, without any friction, it's going to slide down the ramp. That means friction must be opposite of that direction. Now the last force is actually kind of a weird force. The block is sitting on the ramp. If gravity's pulling it down, I have to have a force which is holding it up, so that it doesn't slide through the ramp. And that force is what we call a normal force. And what the normal force really is it's a contact force between an object and a surface. A normal force always acts perpendicular to the direction of that surface. So in this case, perpendicular to the ramp. That's why the term normal force is used. Normal is a term in vector calculus to talk about things being perpendicular to one another. So those are my three forces that act on the block. So when I draw a free body diagram, the things to think about are, what are the types of forces that act on the block, what directions do they act, and what I might also want to do when I represent these forces is try to think about which one of these three is likely the largest. In this case, I've made gravity the largest of the three arrows. It's probably the largest of the three forces. In this case, normal force and friction, smaller arrows. They're about the same size because I don't really know enough about this situation to determine whether normal force or friction is going to be larger. So there are some common types of forces that you come across in a free body diagram. And here are the common types of forces that we deal with on a regular basis. All of these forces can be boiled down into one of your fundamental forces. Gravity, an obvious example of one. All of these other ones really are types of electromagnetic interactions in one way, shape, or form. Tension, you can almost think of it ultimately boiled down as a strong nuclear force, what's actually holding the atoms together. So gravity or weight, I usually use the symbol W to talk about that. And when close to the surface of the Earth, we can actually calculate weight by the mass of an object times the acceleration of gravity g. Now, excuse me, we skipped ahead. Weight and mass are totally different things in physics, even though we use them interchangeably in our everyday language. Weight is a force due to gravity. Mass is how much matter is in an object. Now, in our everyday ordinary life, that doesn't really matter because weight and mass are proportional to one another. There's this factor of 9.8 meters per second squared, the acceleration of gravity in there, that we're really talking about the same thing in everyday life, but in physics we're talking about two different things. Mass is also a scalar, weight is a vector. So kind of keeping that distinction is important. The second of the forces, which we saw, normal force, that's a contact force that results from sitting on a surface. It's always perpendicular to the surface and points up, usually. Friction, I use a little f to talk about friction. That's a force that resists motion, and it can either resist motion as in slowing an object down, or resist motion as in preventing an object from moving to start with. The other two types of forces that we didn't talk about, T, tension. Tension is a pulling force that's caused by either rope, chain, cable, whatever type of object you're pulling this object with. Tension always has to be a pulling force. It can never be a pushing force because ropes, chains, cables can never push blocks and objects. They can only pull objects. And the last one is just a general contact force. This would be when we talk about me pushing the cart along the floor. That'd be a general contact force. I'm in contact with the cart. I'm pushing the cart. And I usually use a big F to talk about that. So those are my symbols that I use. When you see me do free body diagrams and work problems, this is the code I'm going to use to signify weight, normal force, friction, tension, some other general contact force. We'll start to do in the next lesson is look at Newton's laws and what they actually tell us about forces and start to come up with some conceptual framework to solve some problems.